Hello. This is my constant velocity lab, the first lab for physics this semester, or first lab report, or yada yada yada. Yeah, for the intro. Um, yeah, the lab was designed to find the difference between the experimental and theoretical motion of an object moving with constant velocity. In this case, it's a lot easier. We just did it along the x-axis, so it's not changing direction at all. The way we did the theoretical was GlowScript. The way we did the experimental was we just rolled a marker and we used some tracking software to figure out its velocity, its position, stuff like that. We're designed to show Newton's second law, which it did. I'll explain that in a second. The system was the marker or the ball in the GlowScript case, and the surroundings were the desk or the air and everything else that is affecting the marker. Newton's second law is important because this is what the lab was about. The momentum principle. So it's pretty much saying that the net force of a system is equal to the change of momentum of that system divided by the time that takes place. So how do we use that in the lab? Well, we use the velocity update formula in our GlowScript. So as you see in the very bottom, the initial velocity plus the net force divided by the mass times the time that takes for all this to happen will give you the final velocity. Well, as you can see, when there's zero net force, that zeroes out the whole thing, and the final and initial velocity are the same. So that's what we were testing there in our lab. And as we found, it should theoretically be what happens. With the procedure, we recorded a video from straight above of a marker rolling in a straight line. We used a ruler to just make sure it's going straight. We imported that video into a tracking software called Tracker, and then each frame of that video I clicked on the center of mass, and that wasn't super accurate. I'll get into that later, but yeah, we tried. And then theoretically, we just used GlowScript. We wrote some code using Newton's second law, and we built a model. The initial conditions for the GlowScript were calculated based on the experimental data we used, and then I imported both of those into an Excel sheet to get the final graph. Here is what it looks like when I was tracking the marker. Just every frame I'd click that red dot on the middle of the marker, or I thought the middle of the marker was. There was definitely human error there. The top right, you can kind of see that position versus time graph. It's pretty linear. The way we did GlowScript stuff is we took the initial position, the final position, and the initial and final times from the tracking software, which it gave us, which is pretty sweet. If you can look back there, I can't go back. Whatever. Yeah, it was in there. It gave it to us, and then we just did, average velocity to get what we wanted to use as the initial velocity. Yeah, just the formula. Okay. Yep. So this is the code that we use for the GlowScript. The top two things, you can ignore the gray out stuff. The initial conditions from the last slide. The bottom two, the top thing is the velocity update equation, and because there's zero net force, there's zero acceleration, so therefore it's not changing. That's why it's a zero vector. The bottom one is the position update equation. That is, as was also derived in that slide up front. And that's just showing, you can see the initial velocity and how it's changing the position. This is what the final graph looks like. Time versus position. The orange is the theoretical, what should have happened, in a perfect world. The blue is what actually happened. I know it looks like kind of two linear graphs. They're not. The orange is linear. The blue is decreasing exponentially. Even slightly, but it is. That is what's happening there. And you can tell because it matches at the beginning. It doesn't at the end, but it's changing, getting greater. Yep. And then we go to the next slide. Conclusion. Theoretically, the marker would have rolled further, but in reality, it did not. The reason it did not, because there was not zero net force on the marker. There was some net forces. There was the slipping, there was air resistance, and there was friction. Just like saying, possible air supply. It didn't go further. Well, position tracking, I didn't click on the center of mass perfectly every time. That's probably a good point. Rounding errors, I didn't use infinite decimals, and then outside forces, like I mentioned before, friction, air resistance, or slipping, all affected the. So these are the two questions they wanted me to answer. What if we flipped the negative x and the x-axis? Well, magnitude would have stayed the same, just it would have been negative. It would have been a negative slope now. It would have been the distance would have been negative because it's moving backwards. The net force is going to be 0. What does that mean? Well, it means that theoretically there would have been all the forces acting on the marker would have canceled each other out. So it would have been gravity, which is mg, and then the normal force of negative mg, and the normal force of the table pushing up on the marker, which would have been positive mg, and they would have canceled out. Thank you for listening.